Here is 11.5, the alternating series, and we'll learn the alternating series test. This is a brand new test and way of going about it, so I'll introduce with this simple example. What if you have this series from n equals 1 to infinity, negative 1 to the nth power times 2/3 to the nth power? And just to demonstrate what we mean by the alternating series, we mean that the terms alternate between positive and negative. So, right, if we were to look at the first term, plug in the 1, we'd have negative 1 times 2/3, negative 2/3. But at n equals 2, hey, we'd now be squaring the negative 1 and squaring, so we'd have positive 4/9. And n equals 3, n equals 4, and so on. They're always alternating negative, positive, negative, positive. Or certainly, a series could certainly start positive and negative so long as they're switching back and forth. So at this point, I will show you the alternating series test. It turns out that if a series is alternating, it's a lot easier to show that it converges because when you add up the terms, you're adding a positive and then a negative and then a positive, right? So they're kind of canceling each other out as you keep adding. So here's the nature of the test. I'm just going to put the whole thing up on the screen. Obviously, take a moment to copy all that. And most of this section is just examples of what the alternating series test looks like in different cases, in cases where it converges, in cases where it diverges. Okay, so I'll go ahead and read through from the top. Let a sub n be greater than 0. So we're going to think of the an as the non-alternating part, and I made that known, that note at the bottom. When we think of an here, it's like we think of it as removed from the negative 1 to the n, or in some cases we'll see negative 1 to the n plus 1. So the an is the part that does not alternate. So like separate that. Okay, so then we look at the limit as n goes to infinity for an. We need that to equal, if we're going to converge, we need that to equal 0. That seems maybe natural enough. And we need the second part to happen. If the terms are really, they're decreasing. So if a sub n is greater than or equal to a sub n plus 1 for all n. And we write it this way for a reason. Really all we're saying here is that the terms are monotonically decreasing. So the next term is always smaller than or at most equal to the previous term for all n. But there's a reason why we present it that way. And that's it. So alternating series is a way to prove if both of these conditions are met, then that will prove that it converges. There is no way to prove that something diverges by the alternating series test, but we'll talk about that situation in one of the examples, and it turns out it's if one of these fails, then we can fall back on a test that we already know for diverges. Okay, let's jump into it. I've got our first example here. And again, the question is simply, does the series converge or diverge? And we'll look at the example that we started off with. And it really gives you a hint, now that we're learning more and more tests, right? So on your exam, there'll be a big part of it will simply ask the question, does the series converge or diverge? And there'll be multiple parts, A, B, C, D, E, F. And you'll just be shown these different series, and you got to figure it out, which test applies, and we'll talk about what you're looking for with different tests. We've kind of we've kind of done that sort of practice already a couple of sections ago, I think. Okay, anyway, we know here that we're going to use the alternating series test, right? It's always a lot easier when you're whatever section you're learning, obviously you're going to apply those ideas. So how are we going to go about this? Well, first we want to identify the a sub n. And in an alternating series, it's always the non-alternating part. So we remove the negative 1 to the n power. A sub n equals 2/3 to the n. And then we look at the two conditions, right? We have to meet both those conditions to converge. And so we're kind of hoping that both of them will work out. So the first condition in the test is to take the limit as n goes to infinity of our a sub n. And we want that to go to 0 for this to converge, and it does. Okay, right? 2/3 raised to the infinite power. It's going to get smaller every time, right? Hopefully that's clear. Okay, so number 1, check. That does go to 0. And here's the second part. We want the terms to be decreasing, monotonically decreasing, we would say, because they might equal one another. So we're going to say, hey, here's the an, 2/3 to the n. It's got to be greater than or equal to 2/3 to the n plus 1. We look at the next term. And really we're asking this. We're not stating it so much as we want to show that that's true for n greater than or equal to 1. Okay. The n plus 1th term. There's two ways we can do it. We are showing that something's decreasing, which we've done already. You could show that with the derivative. You might show that the derivative of that function is always negative for n greater than or equal to 1. But there is another way to go about it, and with alternating series, this other way tends to be maybe quicker, or because it's an option, where before it wasn't always an option with the integral test. Here, the nature of the things we're working with, a lot of times it'll be simpler than a derivative, some might say, or there's at least a different approach, so we should chat about it. We could use algebra. So I say use algebra to show this relationship plainly, or we could show that the derivative, and I shouldn't say less than or equal to here, actually, because they might equal one another. There might have been no change. Okay, so I'm going to block this half where I showed the derivative way, and I'm going to show you the algebraic way. Seems like whatever way I was doing before, I just plugged in 1 and sort of did a logical thing. That's not... Oh, I get what I was doing. Okay, how can we show this algebraically? I think it's better if we just go from scratch. Couldn't I divide both sides by 2/3 to the n? Right, I could divide both sides by this left side. If I do that, then I'll get 1. If I divide this side by 2/3 to the n, wouldn't that leave me with 2/3 to the first? Maybe I should even note the algebraic way. Divide both sides by 2/3 to the n. So that leaves me 1. And on this side, if I divide by 2/3 to the n, I still have a 2/3 left after I'm done. And yep, 1 is greater than or equal to 2/3. So I've shown it algebraically. And I say show it plainly because this is the plainly, just numbers, right? There's no n involved even. That's pretty plain. That's got to be true. Or the more familiar way to us, probably at this point is to show the derivative. So I've got 2/3 to the x. If I take a derivative, you're seeing all my little mistakes in my own notes. If you remember the derivative style here for 2/3 to the x, it'd be 2/3 to the x times the natural log of 2/3. A lot of people forget that derivative rule. But there's the derivative, fairly simple one. How do I know that that's really less than or equal to 0? Well, because that's a positive number, and the natural log of 2/3 is a negative number. So I'm always going to get a negative answer for x greater than or equal to 1. So I could show that it's decreasing this way. I kind of like this way though. In any case, I have met both of the criteria for the alternating series test. So I can say my series converges by the alternating series. Some people like to abbreviate this AST. I'm fine with that. Alternating series test. That's not going to be confusing to anybody. I like to write it out myself, but some people like AST. Okay, that is part A. I think just where we are time-wise, we're going to stop there. There's our new test. We've got the two conditions once we identify the AN, that the limit as n approaches infinity goes to 0, and that the terms are always decreasing. Just kind of on that note, I mean, if I go back here to the test, before we wrap this one up, this may seem redundant, and maybe you were thinking back there. If the limit goes to 0 and the terms are decreasing, well, if the limit goes to 0 and we're only thinking of an as being the positive part, if the values are getting smaller to 0, of course they're decreasing. Why do we even need this second condition? Well, it turns out there are some cases where the limit goes to 0, the terms are always positive, the limit goes to 0, but you're not always decreasing for all n. So that it's possible for that to happen. Just kind of keep that in mind. For us and the types of questions we're going to look at, it turns out for the series we see, if this works out, this will always follow. We still need to show it because that is part of the test. It's part of the theorem. We got to show both conditions. That said, if this works, this will always follow. And so you know that it's going to happen. It's just a matter of doing it. Okay, we are going to see an example where an alternating series diverges in the next video.